Hey everybody, welcome to the last video for part 2 of the course. So what we're going to do now is introduce an important quantity in studying light, and that is the so-called index of refraction. It's also called the refractive index, so you'll hear me use both terms. So we symbolize it by n, and the way it's defined is as follows. A material has a refractive index of n, and the speed of the light in that material is v, and that can be written as c over n. Remember that c is the speed of the light in free space, that special value of 3 times 10 to the 8 meters per second. So in a material with index n, we know the light's going to slow down, and in fact that speed is going to be the free space speed, c, over the index. Okay, that's how we define this refractive index. So if you think about it, the index of free space must be 1. This index is going to be just a number, right? And it has to be 1 for free space because v has to be c if we're talking about free space. So the index of refraction for vacuum or free space is 1. Now, any other material where there's matter, right, the index is going to be larger than 1 because v's got to be less than c. The light slows down. So this index is going to be a number that's 1 or greater, the index of refraction. So what I have listed here are some typical materials that we'll commonly talk about and their respective indices of refraction. So as I said, free space is 1. Now air is almost 1. It's slightly bigger than 1. And it's going to vary depending on temperature, pressure, humidity, and what particulates in the air. But it's typically around 1.0003. Okay, and any variation is going to be out in this 10,000th place. Now this is so close to 1 that usually what we'll do is say, oh, the index of air is just 1, just like it's free space. So for light, air and free space are essentially the same thing. In fact, the wavelength of light in air, we'll say, is essentially the free space wavelength. Okay? Now, if you get into something like water, then the index does go up, and you can't make that approximation. It's typically about 1 1/3, 1.33 for water. Again, it's going to vary slightly depending on the conditions of the water. And for glasses or plastics that are typically used to make things like lenses or prisms, the index is somewhere around 1.4 to 1.7. So this gives you a sense of typical range of values for the refractive index. And I just have a note here that we will take the index of air to be 1, okay, when we treat light in air. Okay, now let's talk about whether light slows down or speeds up when it goes from one material to another material. We remember that the speed is c over n, yes? So if this material in this picture, this top material, the yellow one, call it medium 1, has index n1, what happens if light enters a new medium, this blue one, medium 2, with index n2? Does the speed of the light go up or go down? Well, it depends on the values of the indices. So if we think about this with that formula, if n1 is less than n2, then according to that formula, v1's got to be greater than v2, right? If n is smaller in the denominator, v is going to be bigger. Okay, so that means the light's going to slow down if n1 is less than n2. Similarly, if n1's greater than n2, then that means v1's got to be less than v2. So it goes faster in material 2. It speeds up. The way I usually remember this is with this sort of short phrasing. If the light goes from low to high index, it slows down. If it goes from high to low index, it speeds up. Okay? That's the way I try to remember that. Now, in addition to a change in speed, there's also going to be a corresponding change in wavelength. The frequency of the light when it goes from one material to a different material, and when I say different material, I mean a different refractive index. The frequency of the light stays the same. The reason for that is it's the electric and magnetic fields. They're oscillating at a certain frequency in the initial wave. Those fields are driving atoms in the material. They're actually driving the electrons to oscillate at that same frequency. And that oscillating charge is what propagates the light wave. Okay, so when the light goes from one material into a different material, the light that gets transmitted into that different material, you can think of as coming from those oscillations of that charge. Well, the frequency of that oscillation is going to be the same in both materials. So frequency of the light doesn't change, but we know that the speed changes, right? So if the speed is changing, if v is changing, but f doesn't change, that means the wavelength has to be changing. So yes, there is a change in wavelength when light goes from one index to a different index. Okay, so how does that work? What's that look like? Well, we can do the similar thing like we did on the previous slide. If n1 is less than n2, we know that v1 is greater than v2. So if v1 is greater than v2, lambda 1's got to be greater than lambda 2, because we have this formula that says v equals lambda f. Okay, and similarly, if n1 is greater than n2, then v1 is less than v2, so wavelength 1 is less than wavelength 2. Now, again, I usually remember this with this short phrase: low to high index, wavelength decreases. And high to low index, wavelength increases. Okay, so low to high index, we know that the light slows down and the wavelength decreases, gets shorter. High to low index, we know that the speed is going to go up for the light and the wavelength gets longer, it increases. So I can give you a little quiz. I found this picture, so I thought I'd give you a quiz. So in this picture, imagine that the light is in medium 1, the top yellow medium, and it enters medium 2. And what they've shown you in the picture is a representation of the wavelength. So you can see that the wavelength decreases when it enters medium 2. So the question is, which refractive index is lower in this picture? Which is the lower index, n1 or n2? Well, look, the wavelength is decreasing. So that must mean the light is going, right, low to high index, because the wavelength is getting shorter. So if it's going low to high index, that means that n1's got to be lower than n2. So n1 is less than n2. Yep, and the lower index is that one for material 1 in the picture. Okay, good. Now, let's talk about how we can relate the wavelength in a material to the free space wavelength of the light. This is sometimes fun to do. Okay, so we know that a medium is going to, or a material, same thing, has a refractive index n. And let's suppose that for this particular light wave, there is a corresponding free space wavelength, lambda naught. So if this light wave were in free space, it would have wavelength lambda naught. In this material, it has wavelength lambda. Well, you can do some algebra on these relationships we have. So I'll go through it quickly. For free space, we know that we could write the speed c as lambda naught f. Okay, now, for the light in the medium with index n, we know we can write v is c over n, and that's equal to lambda f, right? Speed equals wavelength times frequency is valid in both free space and in the medium, but we have to remember that we have different wavelengths. And then here we're using v equals c over n, we're using the definition of the index. Now, what we can do with both of these equations is we can solve them for f. So over here in the free space side, I'm just taking this equation and I'm solving it for f. So f is c over lambda naught. Over here, I'm taking this equation, c over n is lambda f, and I'm solving for f. And then what we can do is say, look, we know that the frequencies in these two materials, right, free space, I guess I shouldn't call free space a material. But in free space, oops, oh my gosh, I'm so sorry. I went up, oh my God, there we go, sorry. Yeah, I shouldn't say free space is a material because it's not made out of anything. But the frequency in free space will be the same as the frequency in any other material. So I can equate these expressions, so I get C over lambda naught is C divided by n lambda. And I can do some algebra and solve for lambda. All right, so the end result of that algebra is if you have an index of n for a material, the wavelength of light in that material is the free space wavelength over that index. That's what I'm trying to get at. Okay, so again, if you know the free space wavelength of the light, then you can figure out the wavelength in some other material by taking the free space wavelength and dividing by the refractive index. Okay, so that's a nice relationship. Okay, in fact, let's do a little example to end this video. So, and I want to point something out too about how we perceive color. Okay, so let's say I have a certain laser pointer. You guys are familiar with laser pointers. And if I turn it on, the wavelength of the light in air is 670 nanometers. Okay? So let's suppose you point this at the side of a swimming pool, but above the water line. So the laser beam is traveling in air and hitting the side of the pool above the water. Some of that light's going to reflect back to your eye. So what I want to know is, what color is that laser spot on the wall? The reflected light that comes into your eye, right? You're going to see that spot on the wall. So what color is that? Okay, well, let's see. What we need to know is, what is the wavelength of the free space wavelength? Because if you remember when we were talking about the electromagnetic spectrum, if we know the free space wavelength or the frequency, we can figure out what part of the spectrum it's in. Well, this is air. So because the refractive indexes of air we're taking to essentially be 1, the wavelength in air is going to be essentially the free space wavelength. So this 670 nanometers, we're going to say, is the free space wavelength. So if we go and look at our spectrum, I just copied and pasted here the visible spectrum by free space wavelength. 670 nanometer puts us in the red portion of the spectrum. So this laser spot is going to appear red. Okay? Now suppose what we do is, now we have the laser pointer and we turn it on, but we send the beam under the water to hit the portion of the wall under the water. My question is, what color is the laser spot on the wall? Okay, now here's a caveat. You are under the water, okay? So you're not allowing the light to reflect and come back out of the water. So if you go under the water and look at that laser spot, the question is, what color does that laser spot look on the wall? So some of the light's reflecting off the wall, staying in the water and entering your eye. Now, if we go and find what the wavelength is in water, using this relationship we have up here, we would take the free space wavelength, 670 nanometers, and divide by approximate index of water, 1.33. And we would get 504 nanometers. So the wavelength of that light in the water is around 504 nanometers. Now, if you come over here and you say, where's 504 nanometers? That puts you in the green portion of the spectrum, right? So does that mean the laser spot is going to appear green if you're viewing it underwater? Ooh, this is where you got to be really careful. It turns out no, because it's the frequency of the light that determines the actual color, that determines the part of the spectrum. The frequency, remember the rods and cones on your retina, the cells are being driven by that electric and magnetic field at that frequency. It's the frequency of that signal that determines the color that we perceive. The frequency, remember, doesn't change, whether it's air or water. So this laser spot is going to still appear red, even though the wavelength of the light in the water is actually 504 nanometers. Okay? It's a little confusing, but if you remember that it's frequency that determines spectrum and color, I think it's easier to avoid that trap. So again, we love to use free space wavelength to determine parts of the spectrum. I think it's just because it's easier to visualize wavelength. You know, I can see distance from crest to crest. It's harder to visualize frequency, something going up and down. And also the frequencies are, for visible light, are huge if you're using hertz, 10 to the 14 hertz. So we like to use free space wavelength when we talk about what part of the spectrum is the light in, but you got to remember that wavelength can change, and it's really the frequency that determines the spectrum and the color. Okay, I think I've emphasized that enough now. All right, I think that, yep, that's the end of this part then. I'll see you in the next video where we begin part 3 of the course. Bye.